Hey class, welcome back to Unit P. We are taking a look at page P6, probability rules and definitions here. And again, you've probably seen a lot of this stuff before, but hopefully this will tweak some memories for you and also introduce you to the notation that we're going to be using here. That's going to be really important. And you might have seen this before where I showed you that at some point we're going to be dealing with ugly formulas that might look like this. And so to be able to write a probability statement well is really important. By the way, that's about as bad as it gets in the course. And well, actually, you'll notice that 1/2 is just the negative of the other, so it's not quite as bad as it seems. Anyways, not meant to scare you off in terms of that, but let's go back here to where we were. And we're looking at probability rules and definitions. So the first thing is what we call a complementary event. And it's written like this: the probability of not A. So that's how we pronounce it, is not A, or the complement of A. So it's shown with a bar over top. And it's equal to 1 minus the probability of A. So I'm using a Venn diagram here, and it's kind of like you're in a big gymnasium and you're looking down from the roof. And so you ask all the people who wear glasses to get into the circle in the middle. So that might be event A. So anybody who doesn't wear glasses is outside of that, and that's the complement of A. If we're talking about catching COVID, you might think that your chances of catching COVID are, say, 15%. That means that there's your probability of not catching COVID is 85%, the complement of that, 1 minus that. So that is what we've got there. An important statement here, and that is that an event A and its complement are mutually exclusive and exhaustive. Remember, that was axiom number 3. Mutually exclusive means that if it's A, then it's not A. That makes sense, right? So, for instance, if you've divided people into people wearing glasses and those not wearing glasses, then if you're wearing glasses, then the complement of that is not wearing glasses. And so you're in one or the other. You can't be in both at this particular moment when we're doing the experiment. And exhaustive means that together they exhaust all possibilities. Right? So event A and then anything else is not A. So together they exhaust all possibilities. Tomorrow we'll either have a tornado or we won't. And it's not likely that we'll get a tornado. The probability is probably 0.00001 or something like that. But there still is a probability, and the probability that we don't get a tornado is 99.9999 whatever percent. Probability of it snowing might be 40% tomorrow. I haven't looked at the forecast actually. And so its complement is 60% that it won't snow. All right, let's move on here and take a look. Suppose there's 10 persons in a room, 4 are males and 6 are females. Also, 5 of these are dressed in white and the other 5 are dressed in black. Now, you might look at this and say, Doug, are you colorblind? Isn't that yellow and blue? And the answer is, yeah, actually. But when you print these things off, they actually look more white and black. So we're going to consider them to be white and black, wearing white or wearing black, and males and females, although I know they are yellow and blue here. Okay, so wearing white or wearing black. Now, suppose one person is randomly chosen from the group of 10. What's the probability that the person is a male? And again, as we go through these, you might want to stop the video, just pause it, figure it out, and then come back and pick up the answer. Now, the other important thing I want you to note here is I want you to start using proper notation, as I mentioned. So the probability that the person is a male is, we would write it as P and then in brackets M. So the event is male. And that is 1, 2, 3, 4 tenths. Now again, you could express that as 2/5, or you could express that as a decimal value 0.5 4, that's fine. I actually prefer it just as 4/10. It makes it a lot easier to mark. And I know that you know how to make this into a decimal or to reduce this, so I'm not going to test you on that. What's the probability that a person is not male? So in this case, we're only looking at males and females. And what I want you to note here is don't just look at them and say, well, that's the females. I want you to look at these as complementary events. So the probability that a person is not a male would be written like this, M with a line over top, is 1 minus the probability that a person is a male. And so that's 1 minus 4/10 is equal to 6/10. And of course, we know that that's in this particular example, the probability that the person is a female. But think of it in terms of not male. What's the probability that a person is wearing white? So again, you might want to pause and then do these next two. Give this a try. I'm going to assume that you've done that. Probability that a person is wearing white is 5/10. Probability that a person is not wearing white would be expressed like this, which is 1 minus the probability of wearing white is 1 minus 5/10. And that's going to be equal to 5/10. This is going to become hugely important when we take a look at the binomial distribution and the normal distribution in the next 2 units. So the whole concept of complementary probabilities, and actually right through units E and H as well, even R. So you do want to learn this part here. Joint events and marginal events. The intersection of events A and B is written as A and then kind of an upside down U. And that denotes the probability that both A and B occur. So the operative word here is and. An intersection of events may also be denoted as A comma B or just simply as AB. The joint probability of A and B occurring is written like this. Probability of A, and then that joint sign, and then B. Now, if you think of this as being a gym floor again, and let's say we're talking about that this is whether you wear glasses or not, and then this is maybe some other event, let's say that the person is female. Okay? The joint probability is if a person is female and they wear glasses. All right? So you can be female and not wearing glasses, or you could be male, and whether you wear glasses or not doesn't really matter in that particular case because you'd be outside there. And so the intersection of the two is where both occur, females who wear glasses. So females and wear glasses. The probability that A occurs regardless of whether a B occurs is referred to as a marginal probability. In other words, just focusing on one of those. What is the probability that I randomly chose a person and they're wearing glasses, regardless of what gender they are? Or what's the probability that I randomly choose a person and they turn out to be female, regardless of whether or not they're wearing glasses? So it's just focusing in on one dimension of the problem here, either event A or event B. So those are the two marginals in this case, and where they intersect is the joint probability, the joint event. The contingency table, or the crosstab table, or if this were in Excel, it would be a pivot table. So all those mean the same thing here then, is used to describe the data that can be classified in 2 or more ways. And so we can write this as a little table. And if you take a look then at this picture back here in terms of the people, again, the white or yellow, wearing people and the blue, or we'll call it black, dressed people, then you'll see that we can actually put it in a table that looks like this. So there's 3 males who are wearing white, and that would be these 3 dudes here, right? There's 1 male who is not wearing white, and that's this person here. And then the females are 2 and 4 as to whether they're wearing white or not. So here's the 2 and here's the 4 right there. All right, so that is a crosstab table. What we notice here is that these are all out of 10, and so we've got these probabilities here. And if you take a look then at the symbols that we use down here, take a look on page P9 here. The events are white or wearing black, and so here's the marginal values right here. So here's the marginal value of wearing white. So regardless of whether a person is a male or female, 5 out of 10 of the people are wearing white, and we saw that earlier. So these first 5, and then 5 are wearing black. And then in terms of males and females, we had 4 males, so 4 out of 10, 40% are male, and 6 out of 10 are female. And then inside here then is we've got the marginal probabilities. The joint probabilities. So 3/10 those are the males who are wearing white. So male and white, or wearing white. And so that's these 3 dudes at the very beginning here again, these 3 guys right here. So that is the joint probability of being male and wearing white. Remember, the operative word here is and. So the joint probabilities occur in the intersection, or the inside cells of the table here. Whereas on the outside, these are all the marginals. So these are the marginals, there and there. And then these are the joint probabilities. Now, a union event is written like this: A with an upside down symbol that looks like a U, and that denotes the probability that either A or B or both can occur. The operative word here is or. So in this particular case, I don't know why this came out the way it did, but let's draw this circle here. So this would be B, and I'm going to use another color here to show that the union is all of this stuff in here. So A or B occurs like that. Now, you might wonder here, why do we use this formula here, that the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B? Why do we subtract that off? Well, the reason is, let's take a look at the probability of A, and we will shade it like that. And then let's take a look at the probability of B, and we will shade it like that. And what I want you to note here is that we've double counted this area here, right in the middle. We've double counted that, because you counted it when you counted A, you counted it when you counted B, and so you've double counted it. What I often do in class is to say, okay, if you are female, I want you to put up your left hand. So all of the females put up their left hand. If you're wearing glasses, I want you to put up your right hand. And so a bunch of people will put up their right hand. Some will be male, some will be females. Now, the difference between the union and the joint probability is the joint are those people are those who have both hands up. That's the intersection of the two. So they would be the females and are wearing glasses. The union is anybody who has their hand up. The problem is that some of the ladies have their both hands up. And so if I counted the number of hands, that wouldn't give me a good idea as to the number of people who are in the union. And so what I'd have to do is to say to the ladies who have both hands up is to say, you know, if I'm going to count you, put one of your hands down, and then I can count you. So we subtract off the intersection, and what we're left then is with anybody who is either female or is wearing glasses. Page P10 here, it says if two events are mutually exclusive, then one precludes the occurrence of the others. There's no intersection, so they can't occur at the same time. Thus, A and B are mutually exclusive events. And so we would say, let's say this is talking about rolling a die. And the experiment is roll the die once, count the number of spots. So if you got a 1, then it means you didn't get a 2 or a 3 or a 4 or 5. So you get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. That's if we were to put them down as 6 circles. It took up all the spaces. Maybe it'd be better if we just simply divided this up into 6 rectangles that contain all the space. But they don't overlap in the experiment. So the intersection of the two then is 0. And that happens with mutually exclusive events. Let's take a look at some examples here. Consider the 10-person probability discussed earlier. What is the probability that a randomly chosen person is either dressed in white or is a female or is both? As soon as you see the word or, then you know that that's talking about a union. So again, stop the video, see if you can figure out this one and the next couple, and then we will take it up. Okay, I'm going to assume that you've done that. And so we're taking a look at the probability that a person is dressed in white or is female. And so that's equal to the probability that a person is dressed in white plus the probability that the person is female minus the probability that the person is dressed in white and is female. So the number dressed in white is 5/10. The number of females is 6/10. So right away you're already at 11/10. And so we subtract off the 2 ladies that are dressed in white. And that's because we counted them when we counted the people dressed in white. We counted them when we counted the females, and so we've counted them twice. So we subtract off one occurrence of those 2, the intersection, and that leaves us with 9/10. In other words, everybody except for that dude in the middle who's dressed in black. Let's take a look at a deck of cards. What's the probability that a single draw of one card will result in either an ace or a heart? If you're not familiar with cards, let's actually draw these out here, what they look like. Oops, that's not what I wanted to do. I wanted black here. Okay. So there are 4 suits. Oops. Okay. There's 4 suits, so we have, ooh, that's not a very good spade, isn't it? Spades, we've got, at the far end, we've got clubs. And then we've got hearts. And we've got diamonds. And what we've got here then is, in each case, we've got an ace, a king, and a queen, and a jack, and a 10, and then all the way down to a 2. I'm kind of showing it with bridge or whist, or poker. So that makes 52 cards. Probably most of you know this, but every once in a while I'll come across a student who doesn't know the cards, and so that's fine. An ace can be considered to be a 1 in some games, like blackjack or something. All right, what's the probability that a single draw of one card will result in either an ace or a heart? So the probability of getting an ace or a heart would be equal to the probability of an ace plus the probability of getting a heart minus the probability of a card being an ace and a heart. So the number of aces is there's 4. 4 out of 52 cards. Number of hearts is there's 13 out of 52 cards. And then in each case, we've counted the ace of hearts. And so we have to subtract off 1 out of 52, the probability that a card is both an ace and a heart. And that leaves us with 16 out of 52. Give an example of 2 mutually exclusive events. Well, I've talked about this before in terms of things such as rolling a die and the number of spots that you get, flipping a coin, the type of weather that you have in terms of classifications, whether it's raining out, whether it's snowing. That would be at this particular moment. That's actually not a great example because it can actually be raining and snowing at the same time. And I think there's a word for that. But so what section of a particular course are you in? A, B, C, D, or Z, or something like that. That would be an example. All of those are mutually exclusive. You're in one or the other. And of course, complementary events are always mutually exclusive, right? A versus not A. We either get a tornado tomorrow or we don't. Those are mutually exclusive events. All right, finally, let's take a look then at conditional events. A conditional event is the probability of A given B. That is, the probability that A will occur given that B has occurred or will occur. So in other words, B is a certainty. And that's actually written then like this down here. Let me change colors here. It's written like that. The probability of A with a vertical line B is equal to the probability of A and B over the probability of B. Now, one thing I want you to note is that the given part is always after the line. So this is A given B. And although that's not that vertical line is not a slash, it's not divided by, it's not A divided by B, that does help me to remember that the B goes in the denominator. So the numerator always has the joint probability of the two, A and B, and then the given part goes in the denominator. It's the marginal event. So the joint probability of A and B divided by the marginal probability of B. And if you want, I mean, you can solve for this guy here, and all you get is this formula down here, like that. All right, let's take a look then at some examples down here. Given the 10-person example, suppose a male is randomly selected from the group. What is the probability that he is wearing black? So in this particular case, what's the given part? Well, the given part is that the person is male. What's the probability that he's wearing black? So that's going to be equal to the probability of wearing black and male divided by the probability of male. That's going to be equal to how many people here are wearing black and are male? 1. So 1/10. And how many people are male? 4. So 1/10 divided by 4/10, or you could just jump straight to 1 out of 4. So of the 4 males, one of them is wearing black. The given part is that we're only looking at the males. Suppose a person wearing white, so that's the given part, wearing white. So given white is randomly selected from the group. What's the probability that the person is female? That's equal to the probability of being female and wearing white divided by the probability of wearing white. All right, how many people are female and wearing white? 2/10. How many people are wearing white? 5/10. And that comes to 2/5. You could jump straight to 2 out of 5. So 2 out of the 5 females are wearing white. One thing I would like you to note, this is really important here, folks, and that is get into the habit of writing the whole thing out. For 2 reasons. One is, I showed you one already, is that the formulas get more and more complex, and so you want to get the symbols right. The second thing is, practically when it comes to marking this thing, is that if I just see the number 2/5, then that's great. I mean, you got the right answer. But what happens if you just make an arithmetic error or something, or you just count wrong or something? If I see this part here, then that shows me, yeah, it's a conditional probability, and then you might grab the wrong number. You might just count them wrong. And if all I see is the answer and it's wrong, all I can give you is a 0. But if I see this, then I look and say, yeah, this person knows what they're doing here, and so on. And so you might lose a mark, but you're not going to lose all the marks. So get into the habit of doing that, please. A group of 300 persons at a holiday resort was polled, and 2 vital pieces of information was gathered about each person. The person's country of citizenship, in this case whether or not a person is a Canadian or an American, and whether or not they own a windsurfer, which when I was in my 20s, that was the most important thing in my life. And then I discovered women. So this is summarized in a contingency table. So we've got whether you're Canadian or American, whether you own or you don't own. All right, let's do some calculations here. Let's see how many pages I've gone to. All right, the first thing to do is to add up the totals here. So going across, we've got 207 Canadians, and we've got 93 Americans, and that sums up to 300. And then summing down, we've got 125 people own a windsurfer, 175 don't own, and so that also sums to 300. So what I want you to note is that all of these are actually divided by 300, right? Now we don't need to write these down because we're just simply going to be using the numbers in the formulas as they come. But it's important to note then that this thing here is a marginal probability. That's the probability that a person is a Canadian. This is the probability that the person is an American. So these are marginals. This is the probability that a person owns a windsurfer. And this is the probability that a person doesn't own a windsurfer. So the stuff outside or in the margin of the tables are the marginal probabilities. On the inside, you've got the joint probabilities. This is the probability of being a Canadian and owning a windsurfer. And then I could do that for the other 3 as well. All right, let's do a calculation here. And again, you might want to stop this, try it yourself before you do A, B, and C. A Canadian is randomly chosen from the group. What's the probability that she owns a windsurfer? What's the given part? That the person is a Canadian. Probability that she owns a windsurfer will be the probability of O and C divided by the probability of C. What I want you to notice is that the only two types of probabilities that occur in the table are joint probabilities and marginals. So a conditional probability has to be figured out by formula using the joints and the marginals. The same actually with a union. So those are the four kind of probabilities that we looked at. I guess you could say 5 if you include complementary events. That's just a complement is 1 minus a marginal. But there's 4 main types that we look at here. So a conditional probability can't be pulled straight out of a table. You have to use this formula here. So the probability of O and C is equal to this guy right here. So what we're doing is we're going to focus in on these guys right here, and specifically there. So O and C is 80 out of 300, and C is 207 out of 300. So the answer then is 80 out of 207. What's important for you to note here is that when you're talking about a conditional probability here, is that focuses us in on just a part of the table, in this case the first row, just the Canadian row. So it's going to be the 80 divided by its marginal, the 207. And again, you don't necessarily need this middle step here. You can just jump straight to 80 over 207. Let's take a look at another one. Person is randomly chosen from the group, and it's determined that the person owns a windsurfer. What's the probability that a person is a Canadian? I wanted to give you this one to show the difference in the way that these are worded. In part A here, it's saying that the given part is that the person is a Canadian. In part B, the given part is that they own a windsurfer. But it's the same joint probability or the same numerator. So the numerator is C and O, or O and C, it doesn't really matter. But what's different is the denominator. So what we're doing here is now we're focusing in on this part here. And we're still looking at that 80 over 100, or 80 over 300, pardon me. But the denominator is the 125 who own a windsurfer. So the answer then is 80 over 125. Finally, let's take a look here at C. A person is randomly chosen from the group, and it's determined that the person does not own a windsurfer. What is the probability that the person is an American? That'll be the probability that the person is an American and does not own a windsurfer over the probability of not owning a windsurfer. So what we're doing is we're focusing in on this column, and we'll be looking at the Americans in there. So that's going to be 48 out of 300 over 175 over 300, or you could just jump straight to 48 over 175. And there you go. What I'd like you to do is do this next one then for homework. We're going to take that up in class, so P13, and we will do that in class, and then we'll get into looking at independence next. So let's stop the